Okay, so I mean, what I'm going to talk today is about the problem of self-correction in the quantum case, or whether one can find or construct self-correcting quantum memories. This is a long-standing problem in quantum information theory, and okay, what I'm going to explain today is some ideas that allow to put a bit more of rigor, mathematical rigor, in the existing results, and that, I mean, I think open new ways in which we can extend this to more and more complex systems. So it's based on 3 works that you have the references here. Okay, and mainly in the last one, I mean, the one that just was posted on the archive, I mean, some weeks ago. Okay, so the question we would like to address is whether there exist self-correcting quantum memories in 2 dimensions. So the belief is that this is not possible, so they do not exist. And okay, I will explain later which were the, I mean, existing results so far. And our results will prove this rigorously, at least for a family of models, which are the quantum double models. Okay, so that's the approach. And I think the nice thing is that while doing so, we will introduce new techniques, and we expect that these new techniques will allow to generalize our results to indeed, I mean, the full set of all quantum, I mean, topological quantum systems in 2 dimensions. Okay, so in order to talk about self-correction, I'm going to follow some, I mean, very nice explanation due to Oliver Lano Cardinal. And okay, I think probably the best definition of what a self-correcting memory should be is a physical system which, I mean, encodes quantum information, but I mean with 3, I mean, properties. First, I mean, for a macroscopic period of time, this means that the lifetime of the memory should increase with the system size. I mean, and I added that it should do it polynomially at least. It should, I mean, the study is done in the presence of thermal noise. And the important thing, and that's the why we call it self-correcting, self-correcting, is that it should be, it should be without active error correction. So I mean, it's just a passive thing. I mean, the memory should be able to act as a memory without any action on it. Maybe the best thing, the best way to start is to think what happens in the classical case. I mean, the paradigmatic example of self-correction in the classical case is the 2-dimensional ferromagnetic Ising model, where we can encode 1 bit of information in the ground state or the ground space of the system that it is 2-fold degenerate, and then all spins up will be our 0, and all spins down the 1. And I mean, if the temperature is small enough, this is known to be thermally stable. But the problem is that it's not stable under perturbation. So if we include in the interaction a tiny magnetic field, this will break the degeneracy, and then, I mean, the memory will be destroyed. And the same is true for any system in which there is a local order parameter. Since, of course, quantum, if we want to store quantum memory, I mean, quantum systems are extremely sensitive to perturbations. I mean, it's impossible to implement exactly the Hamiltonian one wants. It's crucial that our quantum memories are stable under perturbations in the interactions. And that's why in the definition we put before, we included this, I mean, what I write here in red. I mean, it's exactly the same properties. The memory should be there for a macroscopic period of time in the presence of thermal noise without active error correction, but also in a stable way. Okay, so the memory should be stable against small perturbations. Okay, so indeed, then, in order to have self-correction, one needs quantum systems with 3 properties. First of all, they must have a degenerate ground state, so that in those states we encode our, I mean, qubits. There should be no local order parameter that distinguishes between the different ground states, and the system should be stable under perturbations. And these 3 properties are kind of clear indicators of the existence of topological order. Indeed, one can even take them as the definition of topological order. So in a sense, in order to have self-correction in quantum systems, one needs to study topologically ordered systems. Okay, and okay, there is this very nice picture I put here that's taken from a very nice overview article in Quantum Magazine. Okay, so that's essentially by just asking for what we want, we are immediately directed to the set of topologically ordered systems. Okay, now the point is, okay, among all possible topologically ordered systems, which are, I mean, many and with many different characteristics, we like to see which ones are good self-correcting memories and which ones are not. So, okay, as I mean, the official title of the talk said, the idea that we have is that we will address this by bringing into the problem tensor network techniques. And the reason is that tensor networks are, I mean, arguably the best mathematical way we have to describe topologically ordered systems. And in order to explain why, I will explain briefly how to construct topologically ordered systems using tensor networks. Okay, for doing that, we need to do a crash course in tensor networks. And the nice thing of tensor networks is that there is a graphical notation for them, which I call here the box-like notation. Okay, so essentially, tensors are, I mean, collections of complex numbers with several indices. For instance, we have one index. I mean, this is just a vector. If we have two indices, this is just a matrix, etc. And then for us, a tensor will be just a box. I mean, just the letter inside the box is simply the label of the tensor. And the number of legs is the number of indices in the tensor. For instance, a tensor with one leg will be just a vector. Okay, and therefore there is just one index, vi. Okay, and this I is simply just the computational basis. If I have two legs, I have a tensor with two indices, aij. All these are complex numbers, and therefore this is just a matrix. So one can, I mean, identify this with a matrix. And then this is just the objects, and then the basic operation between tensors is tensor contraction, and this we implement by joining a leg. So, for instance, if we join two legs of two vectors, what we do is we identify the indices and sum over them, and that's, of course, if they were real, this is the scalar product. If we have two matrices and we join the outcome, the one leg of one with one leg of the other, one can identify this with matrix multiplication, because what we are doing is identifying the column index of A with the row index of B and sum over that, and that's exactly matrix multiplication. For instance, if we do, we have a matrix and then we plug one vector in one side, another vector in another one, in another side, we have kind of this expression, no? So in the end, with this, with just this notation in which we have boxes, legs, and tensor contraction, we can describe, a lot of systems, and many of them are quite complex, as we will see. Okay, so tensor networks we will deal with are called PEPS, Projected Entangled Pair States, and among them, the easiest ones are matrix product states, which are those which are one-dimensional. So graphically, a matrix product state is just, we have a tensor with three legs, this A, one leg up and two legs left and right, and we just concatenate it with itself, joining the legs, and finally we join the right leg of the corresponding tensor with the other one. No? If we see what we are doing, if we give names I1, I2, In to these legs that remain open, the final thing we have is just a tensor which has all these tensors, all these legs open, and therefore there are I1, I2, In indices, so n different indices. And what we are doing is we are multiplying the corresponding matrices, so AI1, AI2, AIN, and then taking the trace, which is just in a matrix identifying the two indices, doing the leg contraction of the two indices of a matrix, okay? So in the end, this graphical notation that I have up here, I mean, at the level of a formula is just this formula we have here. Okay. And then, okay, there are two different types of legs of indices in this matrix. One is the one that remains open, and this is the physical index, because in the end, as we will see, this object simply lives in the tensor product of the Hilbert spaces associated to these legs. And we can identify this with a state, okay? Unnormalized state, but okay, we can normalize it later. So that's why it's called physical index, because this index corresponds to Hilbert spaces, physical dimensions. The other ones are virtual because they get contracted through the tensor network. And okay, I mean, therefore, I mean, they are called, I mean, virtual indices or also bond indices. And the dimensions, so the number of indices associated to this leg is called the bond dimension. Okay, usually the physical dimension we'll call small d, and virtual dimension capital D. Okay. So associated to these matrix product states that now we see as physical states, as quantum states, there is a particular Hamiltonian called the parent Hamiltonian. And it's a Hamiltonian that will have the given matrix product state as ground state. In order to guarantee this, what one does, sorry, is to consider an operator, I mean, which is self-adjoint. An operator is also can be seen also in the tensor network notation as a box with legs, input legs and output legs, that acting on the tensors that define the matrix product state together with an arbitrary boundary condition, x, this gives 0. For instance, I can take the projector onto the orthogonal of this vector space. With this property, then, it's easy to see that if I plug H, this Hamiltonian, into two consecutive sides of my state, I get 0. Because H is not only self-adjoint, but also semi-definite positive, because I take it an orthogonal projector. I mean, what we have is the following properties that, I take H as the sum in all position of this operator, of this parent interaction, is semi-definite positive, and it gives 0 if applies onto the matrix product state. And therefore, the matrix product state is a ground state of H that indeed minimizes the energy locally. So this Hamiltonian is also what is called frustration-free. The same can be done in 2 dimensions. Now, instead of taking a tensor with 3 legs, we take a tensor with 5 legs. The one that comes out of the screen, this red one, is the physical one, and the other 4 are the virtual ones that get contracted through a tensor network, like that, that we take, for instance, a square lattice. The remaining thing is an unnormalized state that I can, of course, normalize later, and that's called the PEPS. In the same way as before, we can define a parent Hamiltonian, which is, again, the projector onto the orthogonal of what I can generate by putting arbitrary boundary conditions. Okay, and it has exactly the same property. So if I plug this interaction in any plaquette of the lattice, I get, of the PEPS, I get 0. And therefore, I have a semi-definite positive interaction, which annihilates the PEPS, and therefore the PEPS is a ground state of the Hamiltonian. Okay, by imposing extra properties on the PEPS or on the matrix product state, one can guarantee that this the given PEPS or the given matrix product state is the unique ground state of H of the Hamiltonian up to maybe topological degeneracies. Okay, so, and this comes to the question of how to construct topologically ordered systems in PEPS. And the idea is very simple. What we will ask is that the tensor that defines the PEPS has a gauge symmetry, an internal symmetry. So if we start with a finite group, G, for instance, C2, and we assume that C2 is generated by identity and sigma set, for instance, we'll ask that this tensor has a symmetry in the sense that if I ask with sigma set everywhere, the tensor is invariant. Okay, when I mean everywhere, I mean in the bond indices. The physical index is untouched. Okay, something that happens at the virtual level, so it's not something that one can see physically. Okay, it's immediate to see that this property is stable under blocking, under concatenation. So if I put 2 tensors together, and I put sets around the given block, for instance, two sides, I can put in the middle leg 2 sigma sets, no? One and the other that cancel each other, and then I apply the above equation to both tensors, and then I show easily then that this is exactly as doing nothing. Okay, so in particular, what happens is that any contractible loop vanish. So if now these green dots are the sigma sets, if they follow a contractible loop, then by the exactly same argument as in the previous slide, these vanish. What happens with non-contractible loops? So imagine that now I have a loop around a torus. So I have my PEPS in a torus, so I have periodic boundary conditions, and I have this this loop that goes around the torus. Then, by the property of the symmetries of the tensor, I can deform this loop like that, for instance. Okay, but they do not vanish. I can move it, deform it, but they will never vanish. Okay. Moreover, since I can deform these loops, the local Hamiltonian, the parent Hamiltonian I constructed, is not able to see the loop. Because imagine that I have a Hamiltonian term here in which it seems that the loop is in the range where the Hamiltonian is acting. But because I can deform the loop, I mean, this is exactly the same as having the loop outside. And then the Hamiltonian cannot see the loop anymore. So all the states that I can construct by these non-contractible loops are also ground states. Okay, and therefore I have a degenerate ground state. And these ground states, I mean, one can map one into the other by these non-contractible loops that can be deformed, and therefore there is no local order parameter. Indeed, all ground states are the same in every contractible region. So they are indistinguishable in any contractible region. In order to distinguish them, one needs to really do measures around a non-contractible loop. And that's exactly the properties we were looking for our quantum memories. So we have a degeneracy of the ground state. All ground states are indistinguishable locally, and there is therefore no local order parameter. And these things are stable. Okay, this is a much deeper results due to Bravi, Hastings, and Michalakis that show that topological models are stable under perturbations. And exactly the models that I just described in these tensor network pictures are exactly the quantum double models that Kitaev described in his very famous paper about in which he described the toric code about quantum computation by anyons. And in particular, the case in which the group is Z2, as the example I gave before, is exactly the toric code. When the group is non-abelian, the systems are much more complex, and for instance, the elementary excitations, in principle, are even capable of universal quantum computation by braiding them. Okay, so they are candidates to be good quantum memories. Okay, so now it's time to go back to the original question of how to estimate the lifetime of topological quantum memories. Okay, so as I said, one needs some topological Hamiltonian, and we are focusing in 2 dimensions. So let's take a 2-dimensional topological model with some Hamiltonian. For instance, Kitaev quantum double models of a group, or in particular, the toric code for G equals Z2. As we said, what we are assuming always is thermal noise in the weak coupling limit, and therefore the evolution given by the noise is given by a Lindbladian, okay, which is the Davies generator. So if we start at time 0 with some encoded qubit in the memory, and I let the time evolve under this Lindbladian, okay, I'm interested to see how long it takes for the memory to be destroyed. So which is the time in which this rho t essentially has no information about the initial qubit. Okay, since at t equal infinity, all the information is lost, because there in the ground state we have equal weight superposition of all possible ground states. This question can be reduced to the question of how long does it take to reach rho infinity or close to it. And then, okay, we would like to show that there are no quantum memories in 2 dimensions, and therefore, in order to do that, one has to show that the memory time is short, and this is equivalent to the fact that the spectral gap of the Lindbladian is lower bounded by some constant which depends on the temperature, but is independent of the system size. Okay, so that the Lindbladian has a uniform spectral gap with respect to the system size. Okay, so that's what we would like to show, that we would like to find uniform lower bounds on the gap of the Davies generators, which is the weak coupling limit, associated to thermal noise in these systems. Okay, so which were the previous no-go results for two-dimensional quantum memories? Okay, the first result, which is somehow the seminal result that started all this field, or at least the idea of showing that there are no topological memories in two dimensions, is this paper of Aliki, Fanes, and Norodek in 2007, and they show that for a toric code, indeed this is true. I mean, the gap of the Lindbladian is lower bounded by some constant that's independent of the system size. Okay, in 2016, this was generalized for all abelian models, meaning in which the group is abelian. Okay, and then, but the techniques were very much focused on really exploit all the time they have abelian anions, which are of course much easier to deal with. And there were so far no result that was able to deal with the non-abelian case, in which the group was non-abelian. And this is what we proved. We showed, and for that we needed kind of new techniques, that for all quantum double models, abelian or non-abelian, the same is true. So the gap of the Lindbladian has a uniform lower bound, independent of the system size. And we also have a explicit formula in terms of the temperature. Okay, how does the proof goes? So consider then, our thermal state, and what we do is we consider a purified version of it, what is called the thermophile double. So at each side we do a partial transposition, so that now what is kind of a ket bra becomes a ket ket, and we have a pure state, an associated pure state. It's easy to see that because these quantum Hamiltonians have commuting terms, that what we obtain is exactly a PEPS, a tensor network state. One can then show that then the gap of the Lindbladian that we are interested in is comparable to the gap of the parent Hamiltonian associated to this thermophile double state. And then the problem boils down to estimate the gap of the parent Hamiltonian of a PEPS. Okay. This seems a nice simplification, but we have recently proven a theorem that shows that this is also hard in general, so that the existence of a spectral gap, even for parent Hamiltonians of PEPS, is an undecidable problem. Okay, but the thing is that what we have is not an arbitrary parent Hamiltonian of an arbitrary PEPS, is the parent Hamiltonian of a very particular PEPS, which is a thermophile double associated to a topological model. And then we will show that by exploiting this, the particular examples that we have, one can avoid this undecidability result and indeed give a good estimate of the gap of the parent Hamiltonian. The solution comes via a very nice correspondence, boundary correspondence in PEPS that was found in 2013 by Ignacio Cirac, Didier Poblanc, Norbert Schuck, and Frank Verstraete. And the idea is the following. So if we have a tensor network, a PEPS, like the one that we described before, so what I can do is, if I have a tensor network like that, I can, take another copy of it with a conjugation on top of it, okay, and then join the physical leg with each other. Each physical leg are now joined, and now what is open are just the virtual legs. Okay, it's a bit different than what we did before. Okay, now we join the physical legs, and this is called what we obtain at the boundary is a mixed state, and this is what's called a boundary state. It's also sometimes called a transfer operator. So by doing this, we obtain a mixed one-dimensional state that lives in the virtual degrees of freedom. But this is very important by two reasons. First, because this virtual state is the one that mediates the correlations in the system, first of all. And second, this is the one that defines, by some formula, the parent Hamiltonian of the state. Okay, so this object that lives on the virtual degrees of freedom, encodes both the correlation and the parent Hamiltonian. Okay, so now in this paper, Ignacio and co-authors gave numerical evidence that indeed the parent Hamiltonian, by exploiting these properties of the boundary state, that the parent Hamiltonian of the PEPS has a gap if and only if the boundary state is the given state of a short-range Hamiltonian. So and the intuition is because the given state, the boundary state mediates the correlations of the system. and it's a one-dimensional state. And Araki proved that if we have gives a state of finite range one-dimensional Hamiltonian, they have exponentially decaying correlations, and one expects that the exponential decaying correlations of a PEPS is related to the existence, or to the of a spectral gap in the Hamiltonian. No? So that's the intuition behind. Okay, so what we managed to prove rigorously is the following: that if the boundary state is what is called approximately factorizable, then the Val Hamiltonian is gapped. And a one-dimensional state is approximately factorizable if it really can be, if we have divide the one-dimensional system in 3 regions, A, B, and C, we can write this as a product of AB, a state on AB, times a state on BC. Okay? And this is a natural property because if a state is exactly factorizable, this is just an equality, then one can show that the terms in the Hamiltonian commute, and therefore the system is gapped. Moreover, this approximate case reduces to the Martingale condition of Brun-Lafter-Gaelle in 1995, which is, so far the condition with capital letters that shows that a Hamiltonian is gapped. And indeed, this was proven rigorously by Angelo Lucci and Michael Castroiano, showing that indeed the Martingale condition is equivalent to gap. Okay, so essentially, this condition is, roughly speaking, equivalent to gap. And then in a second theorem, we show that given state of Hamiltonians with fast decaying interactions are approximately factorizable. And these two theorems together prove rigorously the result, the conjecture in the Val boundary correspondence paper of Chirac and co-authors. Okay, so in order to, the intuition behind this theorem too is very easy. Imagine that instead of a thermal state, we have really an evolution. So, okay, now we add the complex I here. Then, because the H is local, this evolution by Lieb-Robinson bounds is essentially a finite depth circuit. And if I have a finite depth circuit like that, then this can be seen as the product of some lambda and some omega, which are simply the blue and the red parts of this circuit. Okay, so what we do is much more complex than that, but the philosophy is exactly the same. Okay, so how do we use this theorem 1 that relates approximate factorization with gap in our result? And with this I will finish. So how we use this theorem 1 to prove the main theorem that I'm presenting here about the gap of the Lindbladian of quantum double models, the Davies generator. So far we had this proof I sketched before, in which we reduce the proof to prove the gap of the parent Hamiltonian of the thermofield double PEPS associated to the thermal state. And then essentially what we prove, and that's the technical part of the theorem, is that indeed the boundary state associated to this thermofield double is approximately factorizable. And therefore, by going to theorem 1, we show then that the Hamiltonian, the parent Hamiltonian is gapped, because the parent Hamiltonian is essentially has the same gap as the Davies generator of the noise. Then we can prove that the Davies generator of the noise has a uniform lower bound independent of the system size. And that's the end of the talk. Thank you very much for your attention.
Great. Thank you very much for your very nice talk, David. So we have time for a few questions. So if any of the participants has any question, please just write it on a Slack and I will read it to David. In the meantime, I want to ask you something myself. So all these techniques that you have presented here work for quantum double models, from Kitaev's quantum double models, but have you thought, do you think is it possible that these techniques can be extended to some other 2D models? And
yes,
could you
indeed,
give
Yes, indeed, we are working on that. All known topological models in 2 dimensions have a very nice description in terms of tensor networks, in terms of PEPS. In particular, there is a very nice paper from the group of Frankfurt State in which they do that. They were able to give a PEPS description of all, stringent models. And indeed, we are now trying to follow exactly the same path, but for this more general class which is believed to be all 2-dimensional topological models. But the thing is that, I mean, techniques get much more complicated, because instead of working with the representation of groups, as we do here, we have to work with the representation of weak Hopf algebras, which is, I mean, quite weird mathematical object. We are now currently only at the level of Hopf algebras, but already that is much more complicated. But I mean, indeed, we expect that the same can be done, exactly the same, but yeah, simply that the mathematics will get more complicated. But that's the nice thing of going into tensor networks, that essentially, I think we are in the right language now. I also expect that, I mean, with the same techniques, similar results should go straightforwardly in 3 dimensions. Of course, not covering the HA code, but other codes like the, I mean, 3D toric code and all these things. I mean, I'm pretty confident that exactly the same techniques will prove exactly the same result. But yeah, this is, I mean, work for the future, yes.
Okay, I see, thanks. So maybe for the interest of time, we will move all further questions to the roundtable discussion after Simon's talk. So thank you very much again, David, for your talk, and see you in a bit more than half an hour in the roundtable discussion.